time. So thank you everyone for showing up. I believe we've got quite a few interest here, and you've taken an important part of your time today and decided to join us. We hope this is super useful for you. We are super excited to meet with you all. All right, let's get this kick started. So what are we doing here today? Scaling our data platform. It's a story about DoorDash. Hopefully you all are DoorDash customers. If not, I urge you to use it. It's a pretty useful product, especially if you're ordering food for your family or any other items from the stores that we have. Today, yeah, we've got a packed agenda. So we'll start with an introduction to the platform, data platform. What are we about? What do we do? I will go a little bit into our journey, our story at DoorDash, and how the data platform has evolved along with the business and the growth of the business. And right about 12:20, we've got a series of lightning talk, each from some of our team members here in different areas that you will find interesting, I hope. In the meanwhile, if you got questions, please use the Q&A link in the Zoom channel in your webinar to ask those questions. We will either answer them real time, or we will take some of these answers and answer them live towards the end of the session, which would be the Q&A session, which starts at 12:45. So with that, we can give it a shot. Let's go. All right, introduction. So DoorDash, as you can see the bag, it's a very alluring brand at this point, definitely in the United States and a few countries outside. Hopefully it's something that you all have used. The vision for DoorDash is to, at this point in our business, it's all about optimization. It's about growth. It's about profitability. It's about making sure that our customers are engaged and happy with the product. So what does data do? The data vision here is to collect and gather timely data-driven insights so that we can have a beautiful, flexible, reliable, high-quality data platform. And how do we do that? This is just the vision. So how do we get there? The way to do that is that the data platform aims to enable two communities. One of them, which we call as the data builders, the other one we call as data consumers. And let's try to figure out what this means in our case. All right, so who are data builders? Data builders are our first-class customers. By we, I mean data platform. The main ones there are the data engineers. They are the ones who use the platform to build the right data models, the star schema, the right facts and dimension tables, so that other builders, such as the data scientists or ML engineers or data analysts, as you can see there, are able to build the appropriate statistical models, are able to dive into the business and look at a business from a week over week, month over month, trends, patterns, issues, challenges, etc. So these are the data builders. They are the ones who actually build the data on top of the platform that this particular team that is chatting with you today have provided. And then comes the data consumers. These are the folks that actually these are the humans that actually take the decisions or the insights or the KPIs that are driven by the data builders and use them to run the company, to run the operations, to run the business, to run the product. As you can see, there are business leaders, there are product leaders. The one unique thing about DoorDash is that it's a logistic marketplace, as in it's a real world business doing business in various marketplaces such as Sacramento, Davis, Seattle, Chicago, New York, etc. Well, the operators on the ground are incentivized to make sure that their business runs fantastically well in their area. So they are data consumers as well. All right, so given that, that's the background. So now we will look into the story of DoorDash's scale and growth as it relates to data. All right, buckle on for a great opportunity here. And obviously, if you want to join us after hearing this story, you are super welcome to look at our careers page at DoorDash, or if you visit the DoorDash blog, you will find a lot of information there as well. Hopefully, it's going to be all awesome, and this would mean that you would want to join us in our journey too. All right, so with that, let's talk about the scale and growth. So when we talk about scale, it's one thing to say that, hey, it's large scale, it's all about volume, but let's put some numbers behind to understand what that scale means. So as far as the data warehouse activities go, we've got about 2,500 plus users actively using our data warehouse to the tune of about 5 million queries per day on top of the data warehouse data sets. We've got double-digit petabytes data. And as far as real-time events go, we've got hundreds of billions of messages flowing through the real-time ecosystem today. Alan Wang in the talk today is going to talk about some of those challenges there. The experimentation platform, our monthly number of experiments that we conduct and analyze is around 250 or thereabouts. We have plans to double it soon. As far as the machine learning area goes, yeah, there's 200 plus machine learning models in production. We do about 3 million predictions per second and more. So yeah, that's to give you some idea of what scale is. Okay, all right, so now about the journey. I would like to take you back to about 2.5 or 3 years ago. So at that point in time, all of data platform at DoorDash was 4 individuals, 4 engineers, I mean, 1 engineer managing experimentation platform as you see up there, and 3 engineers managing the one that you see down below called data infrastructure, one of who was an intern who's now converted and joined us full time. But that was then 3 years ago. Fast forward to today, as of now, just within a very short period of time, 2.5 or 3 years, this is where we are. We've grown alongside the business. We've added quite a few boxes, as you can see there. The main ones being real-time streaming. We've added a machine learning platform, experimentation platform. Again, the idea is not to discuss the architectural view here. It's just to point out that companies such as DoorDash, which experienced massive growth and hockey stick growth, the challenges and the interest from a perspective of building the right technical stack is a very, very interesting journey. And that's part of the journey that we would want to take you through today. All right, so what are some of the future initiatives? Well, this is how I'm thinking about. We're talking about most companies seem to do these sort of analytical cron jobs or data or DAG-based evaluation of their ETL pipelines and then spit out a dashboard or reporting at the end of the day. Typically, it's on a daily cadence, typically. Now, DoorDash is a real-time business. We want to make sure how can we make as much analytical data be computed and available to our business and our partners real time? That's one of the initiatives. How do we increase the velocity of our data builder community? If they're doing something, how can we make it less friction for them so that they could do things faster? Talking about that, experimentation velocity. DoorDash is a very data-driven company. Pretty much all of the features that we launch are minutely inspected with a proper A/B test. Caixia is going to talk about some of those challenges today. How can we increase that velocity? And also, as we reach this sort of a scale, operational efficiency becomes very important. I'm going to talk about a little bit about that. And finally, this is super important. Garbage in, garbage out. So unless we have got highly reliable data, trusted by our community of data builders and consumers, we've got nothing. So how do we get there? Is this what's more interesting? So let's figure that out. Let's see how we can get there. So the strategy that I would like to adopt is the following. The challenge that I've given my team is the following, which is be Shah first and be chefs. Let me expand on that and what we mean by that. As far as assembling a platform is concerned, you can do it a couple of different ways. One is if you were to go to a restaurant, if you were to go to a grocery store such as Whole Foods or Safeway, you could potentially look at a ready-made box for you. Every ingredient you need to prepare a meal in the right proportions is there, right there, available for you. You just have to mix them up, microwave it, and ready to go, right? Or else, if you're an accomplished chef, if you know what you're doing, this is not what you want. You want to mix and match, you want to experiment, you want to see what works, etc. So when you build a data platform, both are important. You need to understand your personas that you're dealing with. And for some of them, you want to be ready to eat or be shoppers. And for others, you want to allow for custom mix and match of your ingredients, if you will, from a technology perspective. That's one way of looking at it. The other way of looking at it is that data platform, for the most part, in most companies, have been in the aid of humans making decisions, the CFOs, the CMOs, the CPOs, various business executives making decisions. That's great. That's awesome. Nothing bad. But how can you make it more API driven, consumed by machines rather than humans? How can you make things automated? That is the name of the game. And to do that, data should be an API that can be consumed by other programs so that things can be automated. There are lots of opportunities within DoorDash to reach that so that we could make data and the output of data and insights a lot more useful from an impact perspective when we move from humans to machines. All right, so how do we get there? What are some of the interesting projects we have? I'm going to quote a couple. One of them is a data lake, and the other one is a knowledge graph. Of course, there's a lot more, but given the constraint in time, I just wanted to put two out there. Let's talk about the data lake. So in one of the earlier slides, I did mention we've got many, many petabytes of data in our warehouse, and it's working just fine. But the question is about world growth. We're growing quite a bit from a data volume perspective, and the industry, not just DoorDash, is looking into the idea of a data mesh or a data lake, if you will. Building a data lake is nothing to sneeze at. There are multiple things to do, things to figure out from a technology perspective, from a storage perspective, from a query perspective, from a governance perspective, from the whole ETL perspective. How should we do that? How do you build these things in layers? It's an interesting challenge, and this is going to be at least 1 or 2 years worth of roadmap that we've lined up. So it's an interesting project. Another idea is an item knowledge graph infrastructure. I'll expand a little bit on that. If you were to think about a typical restaurant, right? And if you go sit at a restaurant at a table and you open a menu, how many items do you find as a menu number of items in the menu? Maybe a dozen, maybe 50, and in some restaurants, perhaps 100, right? Well, the amount of data from a volume perspective and complexity perspective is not that high. However, pause and think about a grocery store, about a convenience stores. The number of SKUs in a convenience or a grocery store or a pharmacy is 2 or 3 orders of magnitude higher than the menu items in a restaurant. Well, all of these items are related to each other. If you were to go for eggs, typically you would buy milk. If you were to buy milk, typically you might also buy bread. There's a graph equation going on there. So we could utilize that data, the power of that data, the graph, in the knowledge graph infrastructure for better personalization, better recommendation, better optimization of the business. But to build that sort of an infrastructure, that's interesting, don't you think? So these are a couple of examples that we have coming up. And so what's important for us? The topmost thing that I think about is standardization. I'm a big believer in the paved path or the information highway, superhighway, when it comes to data. In other words, if you go to the next slide, so what happens there is we just talked about volume. It's one thing to feel proud of your organization when saying, hey, we've got petabytes of data, we've got billions of records, we've got thousands of data sets, we've got this, we've got that. The question is, so what? Who cares, right? Until we figure out how to collect all of these and come up with actionable insights that can be used by the company, by the business leaders, by the humans, by the machines, we've got nothing going, right? So that is the name of the game. And typically, companies talk about the OODA loop. So if you want to know what the OODA loop is, it's about observe, orient, decide, and act. And this goes on in a loop, of course, which is the idea is to collect data, to understand the data, to know what decisions can be taken on top of the insights that you've gathered. Not all decisions are actionable. There are quite a few decisions that are interesting, but not actionable. So which ones of them are actionable and how can we take advantage of that? And this loop goes on and on. A good data platform organization is going to reduce the friction in this loop and try to get things faster and faster. When you get there, the flywheel effect takes over and the organization, the company does much better. But in this whole thing, there's one or two things that I would like to mention that are super important. What are they? Let's look. What is the most important feature, if you ask me? Data reliability. As we just talked about earlier, garbage in, garbage out. So unless you got reliability, you got nothing. So how do we get there? Let's figure that out. What is data reliability, first of all? It's about making sure that there are no data issues. There are no outages. And if you were to have outages, now that we're a public company, a very important company that does affect day-to-day lives of our customers, the cost and the impact of it is pretty high. For example, you as a customer, if you were to open the DoorDash app and we gave you an ETA, estimated time of arrival, of 15 minutes or 20 minutes, however, in reality, if it took 45 minutes or 50 minutes, you wouldn't be terribly happy, right? So we would lose your trust in that case. We don't want that to happen. So how can we make sure that there's no loss of trust from our consumers, from our business leaders, from our product managers, et cetera? So that's the name of data reliability. Most companies think about reliability in terms of maturity. So let's see what data maturity means. So you could start with level 0, which is super low maturity, and then graduate your way to bronze, silver, and gold. So not enough time to go through every one of them, but you can see the slide and see reaching the gold would be the North Star. How can we get there? If you got something richly described, strongly governed, operationally awesome, happens at a faster cadence, that is the name of the game, and that's the data maturity level, which we aspire to get to. We're not there yet, to be super honest with you all, but we are on our journey towards that. And Faye Liu is going to talk about just that to start off the Lightning Series round. So Faye, take it away and talk to us about, or chat with us about data quality and maturity at DoorDash. Faye, it's all up to you.
Thank you, Sudhir. Hello, everyone. My name is Faye. I'm based in Seattle. I have been DoorDash and a data infrastructure team for more than a year. Today, I'd like to share with folks what we have achieved, specifically from data quality perspective in the past year, and our future plan. Nowadays, given the growth of the data volume, more and more external and internal data sources, and increasing complexity of the data pipelines, data quality issues are practically unavoidable for data-driven companies like DoorDash. We have many times waking up in the night to deal with data issues in critical ETL jobs back in the company dashboard. There are various root causes. It could be duplication, no data, or schema changes in the service DB were not applied in the ETL script. Data quality issues can cause stale dashboard, inaccurate prediction, and reporting eventually erodes the trust on data. In the next slide, I will share how we measure the data quality. There are 5 dimensions we are following. Freshness, which inspects when the data was last refreshed along its SLA. Completeness, which measures there is no unintended data loss during ingestion or transformation. Row count level check is one way we are doing. Accuracy, which measures the variance between the reality and what's persisted in the data system. Consistency, which measures data remains the same in respective where the data resides. Uniqueness, which mainly detects the data duplication. In the next slides, I will share how we are doing to improve DoorDash's data quality. We break down the process into 4 pillars. Defining ownership and SLA for data sets. We need to have clear agreement on when and how to respond to the identified data issues by who. Building validation and notification tool. Tooling is a fundamental layer for us to get insights of data quality health and know when the data breaks. Creating data quality process for resolving issues. We need to formalize the process to collaborate with responsible parties to triage and resolve issues. Certifying data set and surfacing data quality metrics. This is the last and important step to visualize data quality health and giving data users more confidence before consumption. Now I'm going to go through each of them for more details. Defining owner and SLA. Data owners are responsible party for data quality issues. We enforce the dataset owner as a must-have field when onboarding data quality rules. We also partner with data engineering team to prioritize critical data sets and set clear and detailed SLA, including threshold, who should respond if SLA breaks, and the time to resolution. The next slide, I will share the tooling. To build a reliable and trustworthy data platforms empowering DoorDash's data-driven decision-making, the first step is to build data observability. Borrowing the idea from the DevOps, how they improve the operational excellence, it's essential to be capable of monitoring and alerting, tracking and triaging of data issues to minimize the impacts of downstream. I'm going to share more details about the requirements of the tooling, architecture, self-serve interface, and the integration with ETL. The fundamental principles we're following. Number one, be extensible. The tooling should maintain the ability to easily integrate with API and be scheduled with the way users want. Scalability. The data product should scale elasticity as the organization and the demand grows. Usability. The tooling should be easy to learn and easy to onboard. In the next page, I will share the architecture of the data quality framework V1. Essentially, it's a rule-based validation and notification system implemented with gRPC in calling. It exposes multiple entry points, including user interface, API, Airflow operator, and YAML, and also provide ETL-based and Chrome-based validation scheduler. With rubrics, data notification will be sent to email, Slack, and PagerDuty based on the severity. In the next page, I will share the data quality portal V1. This is a screenshot of the portal built upon the retool. For those who are not familiar with retool, it's a drag and drop UI. It enables a fast iteration for backend engineer. With this self-service user interface, non-technical teams can easily register and manage their data quality rules. Users can view history and execute ad hoc checks without any integration. In the next page, I will share the integration with ETL. The Airflow is our main orchestration platform for ETL in DoorDash. A data quality Airflow operator makes the data quality adoption easier. This page shows the integration in the generic Airflow DAG. The data quality Airflow operator wraps data quality APIs and provides 3 types of data quality checks in the ETL flow. The pre-check on the upstream dependency, pre-commit check on the staging data, and post-check on the target table. Once we have the data quality issues are identified, we also need the process to involve all the responsible parties to triage and reduce the time to resolution. With all the work done above, we finally come to the step to surface the data quality health and verify and tag the verified data sets with different maturity level. Dashboard and data catalog integration are the two options we're taking. In the next page, I will share one of the dashboard, data quality health dashboard we have built. It is powered by the data quality metrics. It can help us easily monitor, track data quality status and issues. We already moved from the state of the reactive to the data issues to proactive for prevention. Now we are in the process of automating the data quality coverage with more programmatic enforcement. As of now, data engineering team already applied data quality rules across 100% of data sources that power the company dashboard with the framework we have built. This will enable more efficient decision-making by proactively identifying data delays and quality issues as they arrive. For our future plan, the top priority is to fix data issues at scale. We want to define out-of-box rule packs at the basic level, which could be applied automatically with minimum human intervention, and also collaborate with machine learning team to build anomaly detection techniques to identify data out of distribution. Second, we need to improve the communication and incident management process for faster resolution and future prevention. And also we want to leverage and integrate with the centralized data metrics repo, data catalog, and data lineage to enhance the root cause discovery. Last but not the least, we want to adopt data quality APIs to understand, for example, costs introduced by the data downtime. As Sudhir mentioned, there is a long way to go. We clearly closely hear from our stakeholders and want to allocate more resources to evolve our system 1% better every day. Stay tuned for more updates. That's all I have for today. Thank you. I will hand over to Alan.
Hi, everyone. My name is Alan Wang, and I am one of the founding members of the real-time streaming platform team. So today, I'm going to give you an overview of this system and basically how we have been able to create a scalable and fault-tolerant real-time stream processing system, which we call Iguazu. And next slide, please. So at DoorDash, real-time events are important data source to gain insight into our business and help us make data-driven decisions. Just to give you a few examples of how real-time events are used at DoorDash. First, almost all events need to be reliably transported to our data warehouse, Snowflake, or some other online analytical data stores with low latency for business analysis. For example, the Dasher assignment team relies on the assignment data to detect any bugs in their assignment algorithm at near real time. And the second use case is the mobile application health monitoring. Some mobile events will be integrated with our time series metric backend for monitoring and alerting so that the teams can quickly identify issues in their latest mobile application releases. And the third use case is sessionization. We would like to group user events into sessions and add session-related attributes to those events so that we can better analyze user behaviors. So to address those use cases, 2 years ago, we started the journey of creating a real-time event processing system called Iguazu. And we determined that for it to be successful, it must meet the following requirements. It should support heterogeneous data sources, including microservices and mobile or web applications, and be able to deliver the events to different destinations. And should be easily accessible for data consumers to tap into streams of the data and build their own processing logic. To improve data quality, we want to have end-to-end schema enforcement and the schema evolution. And lastly, it should be scalable, fault-tolerant, and have low operational overhead. And in the past 2 years, we built Iguazu and scaled to process hundreds of billions of events per day with over 4 nines of delivery rate. Compared to some of the legacy pipelines that we had, the end-to-end latency to Snowflake is reduced from a day to just a few minutes. So in the next slide, I'll give you an overview of the architecture of Iguazu. As you can see, we use Apache Kafka for PubSub and decoupling the producers from the consumers. And we use Apache Flink for data transformation and stream processing. The data ingestion from microservice and mobile clients are enabled through our Iguazu Kafka proxy. For our data consumers, we provide a streaming processing platform based on Flink and support both data streams and SQL APIs. And after the stream processing is done, the data will be sent to different destinations, including S3 for Snowflake and Data Lake. And we also support Keynote for real-time analytics and Chronosphere for operational metrics monitoring. So in the next few slides, I will discuss some of the details of the event producing and schema enforcement. So let's start with events producing. So one challenge we face here is that how we can enable every DoorDash service to easily produce events to Kafka so that we can gain quick adoptions. And the solution here is to leverage Confluence Kafka REST proxy. The proxy provides with us a central place where we can enhance and optimize event producing functionalities. It provides abstractions over Kafka with HTTP interface and eliminate the need to configure Kafka connections from all services and making event publishing much easier, especially on the mobile side. The Kafka REST proxy provides all the basic features that we need out of the box, but to further optimize its performance and scalability, we added our own features like multi-cluster producing, asynchronous events processing, and prefetching Kafka topic metadata at startup. And also to improve the proxy's throughput and availability, we spend a significant amount of time tuning the Kafka producer properties used by the proxy, for example, the linger time and the required acts from the brokers. So that's for producing the event. The next slide, I'll be discussing event processing. For event processing, one key objective is to provide a platform that supports different kind of abstractions for different users. And Flink's layered API is a perfect fit for engineers who are comfortable with writing Java or Kotlin code. They build application on top of our platform using data stream APIs. And for casual users, they can use Flink SQL to process events in a declarative manner. And our platform, no, not yet. Can you go back, please? Thank you. Our platform provides a base Flink Docker image with all the necessary configurations that are well integrated with the rest of DoorDash Kubernetes infrastructure. And for a better failure isolation and the ability to scale independently, each Flink job is deployed in a standalone mode as a separate Kubernetes service. To support SQL-based applications, we create a framework called Riviera, where all the necessary processing logic and wiring are captured in the YAML file, which is simple enough for everyone to read. So the next slide will show an example of such a YAML file. As you can see, this YAML file captures a lot of high-level abstractions. For example, connecting to Kafka sources and producing results to different things. And the process logic is expressed as a SQL statement. So in the next two slides, in the above two slides, we covered the events producing and consuming. But however, without a unified event format, it's still difficult for producers and consumers to understand each other. So from the very beginning, we defined a unified event for events produced and processed in Iguazu. This event format greatly reduced the friction between producers and consumers. For schema enforcement and evolution, we leveraged Confluence Schema Registry as a central place to register and retrieve both arrow and prototype schemas. One challenge we face in the beginning is how we can enforce and automate the schema registration. It is best to register or update schema at build time, so we can detect and reject any incompatible schema changes at early stage. And the solution we created is to integrate the schema registry update as part of the CI/CD process for our central protobuf Git repository. The CI/CD process not only ensures the compatible schema changes, but also the consistency between schema registry and the release protobuf jar files. So far, we covered event producing, processing, and schema enforcement. So what is the key takeaway that we have here? So first, we find it important to create the event processing system with a platform mindset. Ad hoc solutions are not only inefficient, but also difficult to scale and operate. And secondly, picking the right framework and creating the right building blocks is crucial to ensure success. Researching and leveraging the sweet spots of those frameworks dramatically reduce the time needed to develop and operate this large-scale system. And finally, to make the system user-friendly and easy to adopt requires the right abstractions. The declarative SQL approach for stream processing and the HTTP proxy for producing to Kafka are two examples where we strive to make event producing an easy process so that the users can focus on their own logic, but not our implementation details. And there's still a lot more we want to achieve with Iguazu. We have already started the journey of building a customer data platform where we can analyze user behaviors in different ways through sessionization. And better integration with the data lake is another direction we are heading into. Together with the SQL abstractions and the right table format, direct data lake access from the stream processing application diminishes the way between stream and batch applications and provides an alternative to the Lambda architecture. So stay tuned for our progress on these new fronts. So with that, I'm going to hand over to Kunal for feature engineering at DoorDash.
Thank you, Alan. Yeah, that was great. And thank you all for joining us. I'm Kunal, and I work on the machine learning platform team here at DoorDash. And today I wanted to walk you guys through how we pursued feature engineering in a declarative sense at the ML platform today. To set the context of feature engineering at DoorDash, it is quite a critical piece to our data scientists, taking up roughly about 70% of their development time. And why this is important is because we have over 1,000 unique features that are in production today across 200+ models. And like these are typically high cardinality features, especially since we are in the consumer store level spaces. And so sometimes we have going up to 60 billion updates to our feature stores on a daily basis. And often the climate changes for the features to work on. And so they go through experimentation and churn at the rate of almost 5 to 10 iterations per quarter, each one taking a week of development time. So as we can see, like this is a big part of the data science process. But where we began our journey wasn't really the most ideal of places. Data scientists, as the ML platform, we offer a scalable feature store for them to serve their features into production and access them. But the process of getting the features into production is a fairly involved process, all the way from dealing with data infrastructure to create feature ETLs, to set up the offline serving process using their own APIs or Snowflake, data lake, and so on. And then lastly, accessing these features and putting them into the online feature store. And there's many ways in which this particular flow was not really ideal. So if you want, on the next slide, we can see the ways in which this hampered their productivity. There is many touch points the data scientists typically go through, for the feature creation, feature onboarding, feature upload, and so on. And this greatly blocks their development and onboarding velocity. And this also makes our infrastructure evolution quite slow, because loosely coupled system means each component needs to be tested before the infrastructure can evolve. And so this makes scalability not be on par with how our data is growing. And then lastly, we also don't really have a control plane for these features where data scientists can view what's already in production, share these features across the entire org, and then generally upscale their own techniques together. And so we set out to kind of visualize our own ideal workflow? What would an ideal look like? And we established through customer interactions that typically data scientists want a single entry point that automates their entire downstream interaction. If I set the feature lifecycle in one place and have everything else come for free, that's great. One more thing that is important to them is that if some team is developing features that they can reuse, then why do they need to go through the same process again? And that is another piece that we haven't really solved until recently. So with that in mind, we set out and designed Fabricator as the solution that covers all of these pain points. And we do that using 3 central tenets. The first is we have a centralized feature registry that allows data scientists to build their feature lifecycle in a very declarative way, and we'll see that shortly. But we also provide a unified execution environment that allows them to iterate on these features either in dev or prod through the same set of abstraction, the same set of libraries. And then lastly, once they do all of this, once they commit their feature lifecycle to the registry, everything else downstream is automated, all the way from serving these features online or offline, and adding some observability and reliability for their features, or discovering what other teams have built on top of our platforms. So over the next couple of slides, I'd like to kind of do a small dive into each one of these 3 components and explain how this is empowered through Fabricator. The first piece and the entry point is the declarative registry. And this is where the data scientists start. All of their core concepts: what is my data source? How do I want to construct my feature? Where do I want to materialize these features online? What does my life cycle look like? Other metadata like who's the owner? All of these go into simple high-level YAMLs that are persistent to a single backend central registry. And in order to keep these safe towards evolution in the future, all of these YAML definitions are backed by protobufs. And so in that sense, when we add new functionality to our YAML spec, it's backwards compatible. And that keeps the system consistent over the life cycle of the framework itself. But YAMLs is just one stepping stone, right? Like we also need one way to execute these YAMLs. And what if you want to customize how you want to execute your files? And so our core tenet is contextualized executions. Each Fabricator job is designed to run a given context. And the context is informed by your YAML files. So as long as your YAML files contain all the information we need, you could set the executions to run that particular context and think of these as instantiations of the same job multiple times. And this has helped us black box optimizations for each one of your jobs independently and scale that out to all our users. And then lastly, these library abstractions are, just previous slide, 1 second. And lastly, the production and the development environments are identical for all our users. And so this library constructs helps them know that the job will work the same way once they finish their testing process. And then once we put all of this together, and once the the environment is live, the core functionality we offer is integrations. And so on the next slide, we see how how integrations get automated once their features are committed to the registry. There's a lot of things we can provide for free. Orchestrations. Once the registry has all your feature templates, we can infer your DAGs and orchestrate them on any orchestrator of our choice. Dagster, Airflow, all of these are compatible with how Fabricator can orchestrate your DAGs. We can materialize your features as soon as your data is ready without any additional steps to an online feature store of our choice, Redis, CRDB, and so on. Discovery comes for free. Internally, we leverage Amundsen open source to discover the feature graph. We can also automate observability and reliability through different SLA validations, as well as Prometheus metrics for how your features have been performing in production, their drift, and so on. And then lastly, we can provide agnosticism to storage and compute paradigms. As we switch out the storage backends or compute backends to Spark, Snowflake, or in terms of storage, data lake, Iceberg, and so on, you can be agnostic as a data scientist because the YAMLs abstract all of this part away for you. So given all that we've built, where is the feature platform today? We have about 450 daily active jobs producing about 1,800 daily active features and a feature volume of over 200 billion feature values. And so growing to the scale, what did we learn? So it was an interesting journey. And on the next slide, we learned that optimizations are multiplicative. And so the faster the storage gets, the faster the compute gets, you can actually multiply these to get an even greater speed up as a data scientist. And what this helps us with is standardization, and putting these black box optimizations accelerates developments. We have grown 4x or 5x in the number of features we can serve in production through these optimizations. But one flip side to all of this growth is that growth can sometimes outpace scalability. And so one thing we are focusing now on is that now that we've grown so much in our feature volumes, what can we do to improve the scalability and performance of our features in production? And so, yeah, with that, I'd love to hand over to Caixia to talk about our experimentation framework.
Thank you, Kunal. It's so exciting to see the rapid growth in feature engineering. Hi, everyone. My name is Caixia. I'm an engineer in the experimentation platform teams at DoorDash. Today, I'm going to talk about how we build a centralized statistical library to standardize all of the experiment analysis here at DoorDash. So before I go into the technical detail, I would love to share an overview of the experimentations at DoorDash. So DoorDash, we have a culture of experimenting. We have hundreds of experiments running every month to measure the success of either new product features or new operational process, new policy, or new marketing campaigns. So there are like multiple type of experiments that we run here at DoorDash. The most common two type of experiments are user randomized experiments and switchback experiments. So a user randomized experiments is a standardized standard A/B testing where we randomize on either a dasher, consumer, or a store or a support agent. And the second type of experiment is switchback experiments, which is essentially a randomized on a combinations of regions and time. This is very widely used in our dasher and logistic team. So we have a lot of experiments running. However, about 3 years ago, there wasn't much standardization in experiment analysis at all. Each data scientist kind of do their own calculations or build their own tools to analyze their own experiments. The lack of standardizations caused a lot of problems. So first of all, there are error-prone analysis result. In the past, we have found that there are lots of teams fail to account for clustering in switchback experiments, which leads to very high false positive result. Secondly, because everyone's building the same thing over and over again, so there are a lot of wasted effort with inventing the wheel. Lastly, but not least, so some teams here at DoorDash, they run more complex experiments, for example, our logistics team, and they have developed more advanced methodology or toolings to analyze those experiments. However, those learnings are were not easy to share across to other teams in the company. In order to solve these problems, we built the centralized libraries for the statistical analysis called -AB. It encapsulates all of the methodology that we use here at DoorDash and empowers all of the experiment analysis calculations for different use cases. So the library that we built, it needs to meet the following requirements. So the first of all is of trustworthiness. So we need to guarantee that the result of the analysis that we generate is correct. Like, for example, we don't want to see like high false positive because of mistake we make. Secondly, it needs to be accessible to the team. It needs to be easy to use, and it needs to be like different people in the company, they can like use this to analyze their experiments. And it needs to be able to scale the fast growing experiment volume as well. Lastly, it needs to provide a complete coverage of problem domains at DoorDash. We have a various different product domains. So we have logistics and we have merchant, consumer, and they all have like different problems. And also we have a very different type of experiments, different type of metrics here. So we need to have a complete coverage so that our experiments are able to use this. So with those requirements and challenges in mind, we build the libraries. And in the next few slides, I will talk about in a high level what is inside -AB. So on the right-hand side is the high-level architectures of -AB. And -AB is basically takes two inputs. So the first input is the data of the experiments and also the metric data that's like you want to analyze. And the second thing is configuration. It's in a JSON format as the graph show here. So the configuration needs to tell -AB that how this experiment is configured and also what metrics that you want to analyze and some basic information of the metric. With these two inputs, we are able to next go into the data validation step, which we have an imbalance test, flicker test, and also some pre-processing as well. So this is to ensure the data quality before we start to run the analysis. So after the validating the quality of the data, and then we can go into variance reductions. Variance reductions is a technique that can reduce on the next slide, you can see variance reductions. It's a technique that can reduce the experiment length. Historically, we have seen that at DoorDash, by adopting variance reduction technique, we were able to reduce the experiment length by 10% to 30%. And DashAB offers different type of methods for our user to choose from. After variance reductions, it goes into the most important steps of the whole pipeline, which is variance calculation. So we can see here on the next slide that so this is the most important steps in the whole experiment analysis calculations. And because of the extensive methods that we offer in DashAB to calculate variance, so that it makes the supports for different use cases possible. So like I said before, there are lots of different use cases here, and including like there are different types of metrics that like different team they use. We have ratio metric, discrete metric, etc. And also there are different type of aggregations. Some people want to analyze average treatment effect, and some people want to analyze quantile treatment effect. And we also offer interactions analysis between two experiments as well in the library. There are, in a high level, there are three techniques that we use for variance with calculations, and we have a regression-based method, which is very easy to use, and it also works for many different use cases. So that's why that at the early stage of DashAB, that is very widely used. However, it does come with very high latency and also high memory usage. So we now switch to a delta method-based calculations, which is much faster. And we also offer bootstrapping if the previous two technique doesn't work for you. So these are all configurable. User can choose what method they want to use in the configurations. So after the variance calculations, we have a hypothesis testing. We offer two types of hypothesis testing. The first type is the fixed horizon test, which is a standard t-test. It does require the length of the experiment to be decided before the experiment start. So we see a lot of problems on like picking the experiment when they are not supposed to. So that's why that we build sequential testing into our platforms, which can guarantee always valid result, and our experiments are free to look at the result anytime. Yep. So after we build DashABs, we build the experimentation platforms, where DashAB is a central component in our experimentation platform called Curie. On the right-hand side is the architecture graph of our experimentation system. And as you can see here, Curie it provides the interface and interacts with our user, and also handle the queue and the worker. And DashAB takes the inputs from Curie and is responsible for all of the statistical analysis, and then send the result back to Curie to present to user. So this is a brief overview of our experimentation platform. And next, I do want to share some learnings that we have in the past 2 to 3 years when building this. So first, standardization is the key to trustworthiness and velocity of experiment analysis. So after we have the standard tools, DashAB and also Curie, so we see less mistake in experiment analysis. And also the time spent to analyze an experiment is much smaller now. Secondly, flexibility and accessibility are important. So as I mentioned before, there are lots of different products at DoorDash and different type of metric, different use cases. So we really need to provide some tool that is flexible enough for our user to kind of configure what they want to use for their experiments, and what kinds of method they want to choose. Yeah, so that's all I have today. Thank you so much for listening.
Wow, that was a whirlwind tour but this was just a glimpse of various ideas and challenges that the data platform at DoorDash is undertaking. Hopefully this was useful for you. We'll take a few live questions, Q&A questions that we have. I'm super thankful and happy for every single one of you that have stuck with us with this webinar, and I've asked us questions. So let's pick a few of them. All right. Okay. The number one question, given that we've got a ton of questions, is there a way to reach out with questions? post this meeting. So for that, I'd like to invite Ezra to answer that question if he can. Ezra?
Hi, everyone. We'll send out a form for questions for the team in an email. So everyone just check your inbox after the event, or probably on Thursday or Friday.
Awesome. And is this event recorded, and will you share this recording, Ezra?
Yes, the recording will also be sent out in the follow-up email, which will probably go out again on Thursday or Friday.
Fantastic.
We also have a YouTube channel, which I'll share on the chat, which has all the recordings from all the past events.
Wonderful. Thank you, Ezra. All right, with that, we'll take a couple, 3 questions here. One of them is in the area of A/B tests, which Caixia just covered. So the question goes, are the actionable ones those you can A/B test, or are there gray areas and you can speak to at least one such example? So Caixia, could you take that?
Yeah, sure. So there are lots of things that we can test on. So to name a few examples, where like on our apps, we are testing like the ranking of store on the homepage, and also on assignments area, we are testing the algorithm that we use to assign our dasher to deliveries. And there are also like some area that is really hard to run A/B tests on. So like for example, pricing test is hard in some region due to some policy restrictions, and also if we have a new launch in a new market or some like national TV ads campaign, which is very hard to A/B test on. So in that cases, we usually would do some observational study to use some causal inference technique to kind of measure the impact. I hope that answered the question.
Thank you, Caixia. I'm pretty sure it's a large subject and you can go deeper, but let's cover a couple more. One of them is about essentially real-time streaming. So Alan, this question goes to you. Curious if your Flink cluster is fairly responsive in dynamic scaling or elasticity, or if you find it necessary to dial in to well-known daily high watermark levels by and large. Any challenges there in your experience, Alan, as far as Flink and responsive dynamic scaling goes?
Yeah, sure. Thanks for the question. It's a very good one. So right now, for dynamically scaling Flink cluster, we are not there yet. We are actively looking into that. Flink has a new feature called, I think it's called reactive scaling. It's available in their recent releases. But it will not address the issue that you'll be able to dynamically increase or decrease Kubernetes resources. It will only be able to leverage the parallelism, basically dynamically to dial up or down the parallelism depending on how the watermark goes. So right now our strategy is still to monitoring the consumer lag and make sure that if something's lagging behind, we'll try to increase the capacity. And in a lot of cases, some clusters is a little bit over provisioned to make sure that we don't have to do this very often. But moving forward, we have a plan to basically leverage resource utilizations and consumer lag as an indication of how we should be able to increase the resource in Kubernetes or decrease, and we are hoping to do this with the help of Kubernetes operators within Flink.
Fantastic, thank you, Alan. We're almost out of time, so I'll answer one more question and we'll wrap this up. And thank you. So the question goes this way: how do we decide between using SaaS or vendor solutions or open source solutions? I think I've answered a few on live, but I'll give you a simple way of looking at this thing. Depends on the stage of your company, right? So when DoorDash was much younger, we simply went for ready-made solutions that made sense at the time. As DoorDash grows in scale, the volume and the scalability challenges are abound. So we would like to go with open source solutions that are really, really scalable, have been proven and validated. But we also are encouraging of various new ideas and new solutions out there. So it's a continuous evaluation process, if you will. As you've shown you in the few previous slides, when we started out, we had pretty much nothing going on, but over a period of years, we've added more and more interesting things to the challenge. I'll leave you with one interesting thought though. We cannot simply add every possible thing with technology and solution we could think of. The more complex a data architecture grows, the harder it is to operationalize. The more diverse and the more disparate each of these components are, the harder it becomes for the organization. And remember what we talked about, reliability is topmost of our mind. So we try to keep it as simple and as concise and as paved path as I described earlier, and that's the goal. All right, well, with that, super thank you. There's a lot of you that decided to give us your time and chat with us. If you're interested to learn more about DoorDash as a business or a product, or about engineering in general, there's the engineering blog. If you're interested in joining us, our team, or any other team at DoorDash, Emilia has posted the link there to our careers page. And thank you for joining us again.